So we're going to talk about basically simplifying, multiplying, dividing, adding, and subtracting radicals. That should sound familiar. This shouldn't be like, I've never added a radical with another radical before in my life, okay, or multiplied them together. The only difference will be that we may see some different indexes than you worked with before. What are you used to working with all the time? Good. An index of 2, your square root, okay? In geometry, you did tons of simplifying radicals. In Algebra 1, you worked with radicals, okay? Probably even before that in pre-algebra, but now we brought in this new index thing. So the first 2 properties you see up here are something you should recognize as review of those concepts. Same thing works with square roots. If we have 2 radicals that are being multiplied, it's the same as having a single radical with that product underneath it, as long as the indexes are the same. Okay? And same idea for division. Okay? Are we good with that? Okay, so we can separate it or not separate it with multiplication or division as long as we have the same index. All right. Oh, that has writing on it. Don't look. So surprising. Okay.
The answer's 15.
Yeah, the answer's 15. So here, surprise. Okay. So I must have pushed yes, save, when I meant to say no. All right. So, but what I want you guys to do, so the answer's 15. Great, now that you know. But I care more about how you get to the answer. So I want to give you guys a couple minutes, and in your groups, I want you to talk about how you would simplify this. You'll know if you're doing it right or not now that we know the answer is supposed to be 15. But I care about the how, okay? How would you get the answer that's 15? So take a couple minutes, see how people in your group are doing it, and we're going to try and find the most efficient or effective method. Okay, how it is now or after you've multiplied it together? Okay, so one way to do this is take the numbers as they stand right now. And factor them. So this is like 25 times 5. And this is like 5 times 81. Okay, then I can see there's a 3 to the 4th power contained in this result and a 5 to the 4th power. Okay? How many people did it this way? All right. How many people multiplied the 2 numbers together first and then started breaking it down? Okay, so little hint. If right after you multiply 2 numbers together, the next thing you're going to do is break them apart, did you need to multiply them together? No. Okay? So you can think of these as underneath one radical as they are. Oops, 405. Okay. What number did you guys get when you multiplied them together? 50,625. All right. So when you got 50,625, if you did it that way, I could have known that right after I got that, this could break down to be 125 times 405, because those are the 2 numbers I multiplied to get that number. Therefore, I would know that those are factors. So is it okay for me to look at the factors beforehand? Yeah. Okay. Did anybody try to simplify them individually before they then went forward? No? So another method would be, okay, 4th root of 125 doesn't simplify, but the 4th root of 405 could become, so we could keep the 4th root of 125. But given that 405 breaks down to where it has 4 factors of 3 in it, that could be 3 times the 4th root of 5. Okay? And then you could just work with the 125 and the 5 in the radical and get the other 5 once you combine those together. Okay? So why am I pointing this out to you? It's not always best to just multiply it together and make it like the biggest number you've ever seen in your life before you try to break it down. Okay? Not saying that that method doesn't work. I'm saying that keep in mind that since you're then multiplying and factoring and multiplying and factoring, that you can factor before that at one of these other steps to get to that place where we have our final answer, which is there's a factor of 5 and a factor of 3. Nothing needs to be left in the radical, so like you guys said, it's 15. Okay? Are we okay with this? So several different methods. None of them are wrong. Some of them might be a little faster than others, okay? Or may help you in certain situations. Oh, more writing. Don't look at the answers. All right, go ahead and do parts A and parts B. Okay, so let's check, see if we agree. All right, so first of all, agreements, comments, questions on why this radical would simplify with 3x outside of the cube root and 5x squared still inside of the cube root. Good. So there's 1 power of x out here because x to the 5th literally means x times x times x times x times x 5 times. And if we're looking for cube roots, we're looking for factors that they can be to the 3rd power or a group of 3. So 1x outside of the cube root represents how many factors of x inside the cube root? 3. Okay? Yes, Marlon. Good. Why doesn't it need any absolute value bars? The cube root, so we wouldn't have to worry about that. Okay. Is everybody okay numerically why there's a 3 outside of the cube root and a 5 left inside the cube root? Okay. If you're struggling with this, take your number that's inside the radical, 135, and break it down. So like 5 goes in there 27 times. And then remember, you're looking for perfect cubes. Okay, so 27 would be the perfect cube, or 3 to the 3rd power would be the perfect cube. The cube root of 3 to the 3rd power would just be the 3. Okay, so a factor of 3 outside is like 3 factors of 3 inside a cube root. Okay, well, we'll get there and we'll decide where they go. All right, is everybody okay with part A? All right, part B. So you can see that he kind of simplified individually first to make the numbers maybe a little bit easier to handle. So is everybody okay with the first radical breaking down as 4xy square root of 3x to the 3rd? Annika? 4x squared y. Do you guys agree with that? Okay, so notice that we have a power of 3 left inside the radical. How many factors of x is that? 3. But we're a square root, so we're looking for groups of 2. So we have another group of 2. So this could actually be x squared out here with just 1 power of x left in the radical. Okay? All right, is everybody okay with this looking like 5xy squared square root of 2? Annika? Yeah. Oh, yeah, there's a 3 here for this one. Yeah, no, it's okay. All right, so are we okay with so far? So when he multiplied everything together, he has 20. We're going to change this to x to the 3rd, y to the 3rd, 6x. Without this x from it. Okay, so then Justin brought up the point of absolute value bars and if we need them. Now, we should be thinking about them because these were even indexed radicals. So it is possible with the variables included here that there could be something misinterpreted. Okay. All right, so let me ask, how many people think that x should have absolute value bars around it? A couple. How many people think y should have absolute value bars around it? All right, so let's talk about the x. If you had put all the x's together before you simplified, you would have gotten the square root of x to the 7th. If you put a number in here, or in the beginning because there was an x to the 5th, if you put a negative number in for x, is it going to appear negative or positive? Negative, even after you raise it to the power. And then if you tried to take the square root of that, you'd either say, well, I can't do it in the real numbers, or I'd have to use imaginaries. So we don't need to put absolute value bars around x, because it's not like a trick. It's not like, oh, it looks positive in the problem, and then it could be negative in the answer. It would look negative in the problem, too, and you would just, like, not do the problem or something like that. So x doesn't need them, okay? However, y does need them. Why does y need absolute value bars around them? Kayla? Good. In the problem, if you look at it how it is now, or once you combined them, you would have y squared and y to the 4th, both which would appear positive even if you put a negative number in for y, right? Because you'd square the negative and it would look positive. But does y in the answer guarantee that it's positive? No. So some people like to say that you have to use absolute value bars when, in the problem, it was given, the variable was given underneath the radical with an even power, but once you simplified, it showed up outside as an odd power. Okay? Yes? Mm-hmm. They'll write it, well, in the book that we used before, they would write the 3 out here. I'm not going to get nitpicky about that. I don't care. Yeah. Okay? All right? Okay, any other questions about this? All right, somebody explain to me how to do part C. Taryn. Okay. So sometimes this is helpful in a problem, and sometimes it's not necessarily helpful to rewrite it. Was it helpful in this case? Somebody else besides Taryn? So Justin says yes. Someone tell me why this was helpful to us. Todd. Okay, so those will simplify to be x to the 5th. Good. Okay, and 7 goes into 189. Thanks. So that was helpful. And now I have to finish simplifying the cube root of 27x to the 5th. Good. Okay, so the cube root of 27 is 3. X to the 5th power has a perfect cube of x, which is represented out here, but then it has 2 more factors of x, so those are still underneath the radical. Now, the second one, yeah, sorry, Janae. No, I'm not going to make you guys worry about it there, okay? So we'll kind of draw the limit of our absolute value in the simplifying, multiplying realm of things, okay? All right. So in part D here, it's already set up as one radical, so can we simplify? Yeah. All right, so we get x to the 4th over 8yz cubed. Okay, what would you guys do next after this? Justin? Are you guys okay what Justin has done so far? Okay, so all he did was simplify the top and bottom separately, which he's technically allowed to do because that's like separating it into 2 separate cube roots that he simplified. Are we done? We need to rationalize the denominator. Who thinks that they know the right procedure to rationalize the denominator? Max. Okay. So he has the right idea. Yeah, okay. So I'll tell you right now, put this problem on a test, I'll trick everybody. No, only if I put it on a test before I taught it to you. This is what we've been well trained to do, because what radical has it been with that we've been working with our whole life so far? Just with an index of 2. So when we use square roots, and they're like, and they taught you like, oh, rationalize the denominator. How many of you guys, let's be honest, it didn't boil down to a mathematical explanation. It just boiled down to multiply by the same thing that's already there. Yeah? Okay. Why did that work in this case? Okay, because there's only 2 factors needed because the index of our radical is 2. So we would, if you always multiplied by the same exact thing, you would always make this nice little group of 2 that would simplify. But that's because the index for these radicals is 2, even though we don't write it there. So now we have to step up our actual thinking about why that worked. In this case, we can't just all of a sudden do, hey, multiply by the same thing every time. Annika? Good. Okay. Does everybody get why she's choosing to include 2 factors of y instead of 1? Perfect. Okay? We have to make it a perfect cube root, not just multiply by the same thing, multiply by the same thing. Okay? That's not going to cut it anymore. All right? We've got to think about the index. So in this case, what we would get is we'd get 2zy in the denominator, or yz, when I write it that way. And then we'd have x times the cube root of xy squared. All right, so I want to pose a question to you guys. I'll wait a minute so you guys can copy this down. All right, so what Marlon's saying is he's saying not this. He's saying this. Is that fair? Yeah, okay. Does it necessarily have to be all of that? No. Okay, so how can we simplify this a little bit so we don't have to simplify as much at the end? Not that that's not perfectly fine. It's perfectly fine, and then you would simplify at the end. Okay? Steven.
What I would put in there for it to be fully simple for both things would be 5xy squared.
Are you guys good with that logic? Yeah? Okay. So the 5 would make the 125 now have 5 to the 4th power. X to the 3rd and another power of x would be x to the 4th power, and y squared times y squared would make y to the 4th power. Is that okay? Just to get you thinking about if there's a number involved, then you have to think a little bit harder. Okay? If the number was even a little bit trickier, and what I mean by trickier is something like just say 18. Okay? So I could put the number here to be 18 to the 3rd power, right? So that I have 4 18s, and then I can take an 18 out. But you don't always have to use the entire number to that power. Think about what 18 is broken down. It's basically 3 to the 2nd power and 2 to the 1st power. So how many more factors of 3 would I need? 2 more. And how many more factors of 2 would I need? 3 more. And then whatever this number is the number that I need to use there. I'm just showing you different ways that you can analyze, because if you have to do something by hand, it might be doable like this. It might not be doable if you have like 18 to the 3rd power or something like that. That's a little bit scary. All right, any questions on this? All right, there are 2 problems up on the board. One can be simplified and one cannot. Which expression up there can be simplified and which one cannot? Amy. Okay, good, but I can barely hear. The first one can because what? Good. The thing in the radical is the same, the radicand, yeah. What else has to be the same about the radicals for us to combine them together? Janae? The what? The thing in the beginning, Molly? The index. Okay. In order for us to combine radicals together, the radicals need to have the same radicand and the same index. Just like you can't combine 5x squared with 8x just because they both have x. Okay? They have to have the same power and the same variable for you to combine. Same thing here. You need the same index and the same and the same radicand. So here, when we combine them together, we would get an unchanging radical. And we would just say, but the coefficients become 14a plus 5a, which is 19a. Just like adding coefficients of like terms with variables, but this time they have radicals attached at the end. The radical has to have the same radicand and the same index, which is why in part B it already is simplified. There's nothing further we could do because they don't have the same radicand in that case. Okay? It'd be like trying to add up rad 2 and rad 3 without turning them into decimals first. All right? Objection to me changing it? Okay. Oh, we're not going to do this one right now. Sorry. We're just going to stick with the basic operations for right now. All right. So here are 3 radicals being added together. The plus is they have the same index, so possibly they can be added together. How they look right now, it seems like we can't add them together. Advice? Okay. Simplify. Okay. So take each radical, break it down, and see what you have. So when you simplify the square root of 28, you get 2 rad 7. When you simplify the square root of 175, 5 rad 7. And when you simplify the square root of 63, you get 3 rad 7?
It would be 0.
Good. Okay. Yeah, so when we add them up, 2 plus negative 5 is negative 3 plus 3 is 0. Do I write 0 rad 7?
No.
No. Ridiculous. I just write 0. Okay? But you at least understand that if it wasn't 0, you would write the number and then the rad 7. Okay? Now, if not all three of these simplified to be the same thing, you would combine the like terms together that you could, and you would leave as a separate term the term that could not be combined with them. Just like if you had 5x squared plus 8x squared minus 2x, you would get 13x squared, and then it would still just say minus 2x, right? Because that couldn't be combined with the other ones. Okay? All right. Multiplying. Go ahead and take a minute and multiply this out how you normally would, a pair of binomials. Okay? The operation is not going to change. You're using distributive property or FOIL, whatever acronym you like to use. But let's just see if you can get it right with radicals. Okay, so check your answers. So first thing, if you aren't multiplying the right pieces together, then check back with your technique for distribution or with FOIL. Now, if you're multiplying the right pieces together but not getting the right answer, let's make sure we understand why. So here, 1 times 4 is 4. 1 times negative 3 rad 7 is negative 3 rad 7. 2 rad 7 times 4. The 4 is not in a radical. It can only multiply the other number that's not in a radical that it's multiplying with. So the 4 times 2 are creating the 8, and the rad 7 is the only number in the radical. Therefore, it's staying rad 7. Okay. Then at the end here, 2 rad 7 times 3 rad 7. The 2 times 3 is how she wrote the 6 right here. And square root of 7 times square root of 7 would make square root of 49, or 7. So these radicals are like terms, which are combined together to make this radical. And then the 7 is no longer in a radical, so we get that constant that can be combined with this other integer constant. And we get negative 38 here. Okay? So this is our solution. We can't combine those two pieces together. That's it. Annika? Sure. Okay, when you say coefficient, are you referring to the one that's an integer versus the one that's not an integer? Okay. So it doesn't matter. You'll probably most likely see people write like negative 38 plus 5 rad 7, but it doesn't matter. Okay? All right, in part B, same procedure took place. Okay? Difference is that when we combined together the middle two terms, they canceled out. Okay? So we had 25 minus 18, which left us with just 7. Does this process remind you in part B of anything that we've seen before? Nothing at all? Where's the T-shirt? Where's the T-shirt?
The get real.
Yeah. Yeah, okay, the get real idea, right? That we could take these two imaginary numbers, okay, and as long as they were conjugates, they canceled out the middle imaginary parts and the end part became real. This kind of mimics that idea, except for instead of, these were all real numbers to begin with, but it's just about do they become integers or do they stay in radicals. So the radicals get canceled out in the middle, and the end number becomes an integer instead of a radical. That's going to be helpful for us in the next set of problems, which are the last set, I believe. Okay. So what's wrong with these problems? Okay, it's not just multiplying. Yes. They have a radical in the denominator. So we have this fraction. Maybe it's simple, maybe it's not. We can't really tell, and it's not written in the proper way. So think back to your imaginary numbers for a minute. When we had something like 4 over I, or maybe if this was even like 2I, and we wanted to, I should make it 3I so they don't go into each other. Okay. This was 4 over 3I, and we wanted to rationalize the denominator. We would multiply by just something like I. I would be in the numerator. We'd get I squared in the denominator, which would make that negative 3, and all would be fine. Okay? That's very similar to what we were just doing in the last lesson with the denominators that had radicals in them. If it was 2 times the cube root of 3 or the square root of 3, I would multiply by whatever extra factors I needed in the radical to get rid of that radical and leave me with this expression. Maybe. Okay. Right? Very similar to what we did before. We just needed a single radical with the same index, but we had to wisely choose the factors. What did we do when we came across this situation then? How did we get rid of having imaginary numbers in the denominator there? Molly? Good. Okay. We use 2 plus I. What did we call that? Anybody remember what it's called when you keep the first term the same and you just use a different sign with the second term? Good, the conjugate. Okay. So this was the conjugate of the imaginary number, and then it worked out all nice that when we multiplied out the denominator, the imaginary part canceled out, and we got a real number there. So what do you think we're going to do when we have something like 11 over 6 plus rad 3? Janae? Good. We're going to multiply numerator and denominator. Sorry, it totally looks like a 4. It's 11, but it doesn't look like it. We're going to multiply numerator and denominator by the conjugate of 6 plus rad 3, which would be 6 minus rad 3. And like we saw in the problems that were just done, in the denominator, as I distribute or FOIL this, I'm going to see that I get 36 minus 6 rad 3 plus 6 rad 3, and this should make me very happy that those things are going to cancel out. Okay? And then I'm going to get minus 3. Yeah, Marlon? Yeah. No, that might be the simplest way to write it because it's a repeating decimal. But normally, if they say leave pi in your answer, then you'd probably just leave it like that. If otherwise, they would ask for it in decimal form because it's kind of weird to have a decimal within a fraction anyways, even though it's represented by a symbol. But you actually see pi in both numerators and denominators in formulas and stuff like that. Yeah. I mean, it's technically proper to rationalize it, but with pi, there isn't really a way to rationalize it. So that's why they would just leave it there. Okay. All right, so in the numerator, we get 66 minus 11 rad 3. So these cancel, and we end up with 66 minus 11 rad 3 over 33. Are we good? No. Okay, divide by 11. So both terms in the numerator as well as the term that's in the denominator have a factor of 11. Therefore, I can simplify. So when I simplify, I get 6 minus rad 3 over 3. Can I simplify further? No. Okay? A lot of people want to say, well, look at these 3's right here. Can I just cancel them out? No. Okay? You can't just like jump something inside a radical. A 3 inside a radical is a lot worth a different value than a 3 outside of a radical. So pay close attention to that. Okay? Any questions about this?